We've taken a quick look at Java and programming languages, but there's a lot of terms out there that are useful for us to know as new programmers. So here are some vocab terms that I think are essential, right, to starting our journey into programming. Not just Java, but programming in general. So some ABCs of programming. So computers, of course, that's a great place to start, right? So computer is a programmable electronic device that does four basic things. It's going to receive input, so that's data going into the computer. It's going to process that data, so it's going to do some kind of operations, typically some mathematical operations on that data, and then it's going to provide output. So once that data has been processed, it's going to present the results of those operations, right? It's going to transform that data. Once that data has been processed, we do typically call it information, as we'll look in the next slides. And then if we're going to be using computers in a meaningful way to solve complex problems, we need to hold on to that data, right? It can't just disappear every time we're presented with new data. So a computer typically will have storage to save that data for future usage. So what is data exactly? What do I mean by data? It's the raw, unorganized facts, that are processed, stored, or transmitted by a computer. Once that data has been processed, we call that information. So once it's information, it becomes the opposite, right? Organized, structured, in a way that has meaning or value. Let me go ahead. I'll make sure to fix that typo. So information is derived from data. So information comes from data after it's been interpreted, analyzed, and contextualized. So computer data can exist in many different forms. It could just be instructions telling the computer what to do. And as we know, right, it can represent text, graphics, audio, video, all sorts of things. Another key term is I/O or input output. As we saw right in the basic functions of any computer, input and output are two of those basic functions. So input, we're referring to the data or instructions that are sent to the computer. So this is what goes into the computer. Output is the results once that data has been processed. So that's what comes out of the computer or the process results. It's whatever's returned. So we're going to be using that keyword return actually quite a bit in our programming. Just know return right is referring to the output. So hardware, of course, we're working with a computer, right? Computers aren't just, we've talked about we hear about the cloud, right? We hear about the internet, and sometimes it feels like it's this floating, almost like massless entity, right? That we all use and we all plug into. Although a lot of things work wirelessly these days, there's always going to be some kind of physical hardware, right? That not only makes the internet run, but that also makes our software run. So hardware is the physical components of a computer or electronic system. In fact, if you took my 101 class, I go into detail, right, about the hardware that makes the internet work. So sometimes we think of the internet, right, as this wireless entity. In fact, there's cables connecting continents together, server computers that make it possible for us to get the resources we need. Hardware is really the life, right? The actual physical things that make all the technology we use actually work. And it's been hardware innovation, right, that has made computers so small and pretty much fit now in the palm of our hands. So again, these are the tangible parts of a computer. They work together to make sure that your device or your computer works. They're also essential, like I said, for making software work. So if you want your software to tell the computer what to do, you need the hardware, right, for the software to communicate to. So notice the difference. Hardware is things you can hold. Software is going to be all those things you can't hold. So examples of key hardware components are going to be CPU, that's the brain of the computer, memory, that's going to be for ephemeral data, things that you need to process really quickly, data that you don't need to hold on for long term. If you do need to hold long term data, then there's storage. These can be often confused, right? Just know memories for quick use data, right? Short term data. Storage is for long term data. And then motherboard, that's going to help all these components work together. And then there's I/O devices. So those are devices that just make the computer easier to interface with as humans, right? Back in the day, the only way you could interface with a computer, well, if you go way back when, it was plugging in different cables to get the computer to do what you wanted to do. And then it was command line, right? You had to have intimate knowledge of all these commands that to a human were meaningless, but to the computer would have it execute something. Nowadays, we have all these nice little buttons, icons, and then we can interact with those buttons and icons with our keyboard, our mouse, and now even touchscreens. So software. So software refers to a collection of instructions, data, and programs that tell a computer how to perform specific tasks. So again, hardware is the things you can hold. Software, you can't really hold that. It's more about what getting the computer to do something, and that's what software does. It's the instructions. So unlike the hardware, right? It's intangible. Software exists as code, as scripts, programs, instructions. They're pretty much telling the hardware what to do. There are different levels of software, as we've seen. There's different levels of programming languages. Abstraction is a common kind of a common thread in technology, especially in computers. And it's what's made computers easier to use and also easier to program. So we have something called system software that sits in between a lot of the application software we use. Again, if you took my 101 class, I'm going to say that a lot in all of my intro classes. I always think it's a good idea to get the fundamentals of computers right before we, maybe start getting into actually programming them. But it's okay if you haven't taken it. But always highly recommend, right? You do take that 101 class. But yeah, I go into detail about the different types of software, the OS versus the application software. So application software is like Word, Excel, TikTok, Google Chrome. That's application software. It's going to execute a very specific task. And then right beneath it, there's actually an operating system, or sometimes called system software. That's what makes it easier for those general purpose apps. So those general purpose apps don't have to worry about what computer they're running on. They just talk to the OS, and then the OS will talk to the hardware and get the hardware to do, what we want it to do: show the pixels on the screen, play the audio, the music we want it to play. The mic, right? I'm talking to a mic right now. Without the operating system, which is a lower level of software, this would be supremely more difficult. As we saw with the birth of Java, right? When it was first written, a lot of programmers had the problem of having to code to specific platforms. OS is an example of a technology that has made it easier for us to develop general purpose software for all sorts of devices. So yeah, they enable computers to perform a wide range of functions. Could be anything basic like just managing your files, right? Your pictures, your documents. It could be something more complex like multitasking, right? Running many applications at once. If you're a gamer, right, then that's going to be some pretty compute intense applications. Something interesting that you could do with software is also build new software, which is kind of hard to wrap your head around. I remember when I realized that as a developer, I was like, whoa, like I'm using software to write new software. Maybe that's not fascinating to you, but to me, that's like, wow, like that's almost like Inception. Like, but yeah, there's software for pretty much anything is what I'm trying to say. So synonyms for software, so other terms we'll throw around are apps, applications, programs, scripts. Sometimes people refer to them as executables, as instructions, as applets if it's like a really small app that does like a really like small task. All sorts of terms out there. It's good to know just a few of the popular ones. And for us, we're going to be writing something called source code. So source code is the human readable version of a computer program written in a programming language by developers. Now, it's not always human readable because I've read through source code from other developers on the job. And sometimes the way they write their code, it's like not even a human can read it. But of course, right, compared to machine code, which we'll discuss in some of the next slides, source code is definitely a higher level, right, of code. So it's meant for humans to read. It's going to have all the instructions, functions, statements. These are all terms we'll become really familiar with over the course of this class. So source code is the foundation of all software. However, it does have to be translated, right, before it gets to the computer, because computers don't read this human version, right? Source code is for humans. Machine code is what we call the code that actual computers read. And the one doing that translating is going to be a compiler or interpreter. So before it actually reaches the the CPU, it's going to have to be translated into machine code. Otherwise, the computer won't know what to do. Another term we've probably heard this a lot in tech, especially in social media, right? We're about the YouTube algorithm or the Instagram algorithm. Well, an algorithm, by definition, is a step-by-step set of instructions or a well-defined procedure for solving a problem or performing a task. So this is a fundamental concept in computer science and in math. So algorithms are used to process data, perform calculations, automate tasks, and even make decisions. So that's when we're talking about those YouTube, Instagram algorithms. Those are typically algorithms that follow a certain predefined set of rules. A programmer decided what rules it should follow. And then ultimately that program, that software will make a decision. That algorithm will have some kind of output. So example of algorithms include their sorting algorithms. Those help us arrange data in a specific order. That's what makes it possible for you to get your social media feed in the order of newest to oldest, right? That would be terrible, right, if it was all just jumbled up. It also enables us, right, to sort files, right, on our operating system, right? You always want to see the newest files. Well, there's probably going to be some sorting algorithm employed there. More cutting edge, there's machine learning algorithms. So now we're using machines to learn, right? To learn from analyzing data. They're going to recognize patterns and be able to make decisions on new data, right? And potentially predict things, potentially identify problems. We're using machine learning in all sorts of sectors, in health, in computing, in physics, pretty much everywhere these days. And then, of course, something more familiar, like I said, social media algorithms. Those decide what kind of content that you see. Something we're going to be doing a lot is debugging. And for a lot of us, this is the most painful part of coding. As I've developed into a proper engineer, I've come to love debugging. Debugging is actually where you learn the most about coding. I find that in putting errors in your code and identifying them, you learn about what not to do in the future. Every time you make a mistake, you're going to learn something. If you get your code right the first time, every single time, you're probably not going to learn that much. If you make little mistakes along the way, you're going to be able to identify things that you missed the first time. And then when you come back to a similar piece of code, you're going to know, oh, you're going to carry that knowledge and you're going to avoid those pitfalls in your code. And debugging, there's lots of types of bugs. It's not just writing, the code in the wrong syntax. In the next slide, we'll actually explore the many different various types of bugs that you can encounter when writing software. So yeah, it's a critical part of software development, critical part of maintenance. If you're, any enterprise application, any real world software that's being used out there has to undergo maintenance, right? Because software, just like humans, right? Because humans are making it, right? There's going to be mistakes, and then we're constantly improving it. So we're constantly introducing new bugs into our code, into our software. So debugging it goes hand in hand with making software. You can't make software without also debugging it. So it's an essential skill for software developers, and it's a critical part of creating high quality, reliable software. So ideally you debug, right, before you hand that program over to your user. Maybe your user finds the bug and then you have to go back, right, and fix it and give them that updated version. So some common types of bugs you're going to encounter. Of course, there's the syntax errors, right? These are the ones we're going to make a lot as beginner programmers. So that's mistakes in the code's syntax or the structure. So in Java, for example, we typically end our statements with a semicolon. If you forget that semicolon, then the compiler is going to identify that as a mistake, especially if you continue with another line of code. If you're writing in Python, that's not a syntax error, because in Python there are no semicolons that you have to worry about when writing your codes line by line. So fortunately, like I said, these errors, because they're kind of like language errors, and the compiler is the translator of those languages. Remember, the compiler will translate your source code to machine code. That translator is going to be like, oh, hey, I found a mistake here because I can't translate it. So these mistakes, you typically find them very quickly. The ones that are a little bit harder to find are the logic errors. So that's when your code runs just fine, but it doesn't do what it's supposed to, right? Maybe you're calculating something, and then you find at the end that the output from your program is incorrect because maybe you were able to verify through some other means, right? Uh, Typically, right, we call that testing when you have a expected result, but that's not the result you get. We usually find that through testing, right? So yeah, compiler won't catch that. That's going to be the programmer's job. And again, testing is one of the best ways to find those logic errors. There's runtime errors. So maybe your code runs, but it encounters a specific scenario, a specific input. For example, maybe you divided by zero. The computer will go crazy if you try to divide by zero. So this will crash the program, or it'll trigger something called an exception. That means that you try to do something that is just not possible for the computer to do. So integration errors, that's a little bit higher level once you're further along in your skill set, once you're building more complex systems. When you're putting different parts, different programs together, different tools, you might get integration errors. An example of that could be APIs. So APIs are how software communicate with each other. If that software doesn't, work well with each other, if you didn't program it correctly to work with a specific API, then that can trigger an integration error, for example. So not entirely required for our class, right? But here's a little video that I thought was kind of cool. Just general questions that people on the internet had for a Stanford computer scientist. So someone really experienced in computers. As always, right, with these videos, you can just click on this play button. It'll open up a new tab so that you can watch it. So yeah, go ahead and watch that video. And when you're ready to come back to this one, we'll jump into a little bit of the history of Java.